Okay, so first of all, before getting started, just thank you to the organizers for having the opportunity to come here, to learn, to visit, to meet some people, and so on. Just so you don't get frustrated before I start, I have to tell you that there won't be any epsilon in the presentation, right? So don't feel too lost. It's in 3 parts. This is a small part. This is the main result, which may take the longer. And this is just a corrector result, which is a bit outside, but will have some things to do with the second result, right? So to get started with, here is the framework. We are taking omega-1, a star-shaped domain in Rp, where P is in between 1 and n-1. Omega-2, a Lipschitz-bounded domain of Rn minus P. And we set our cylinders, omega L is L times omega-1 times omega-2. And this is the infinite cylinder in which L is infinite. We separe X in X1 and X2. We define those 2 spaces. For those who are not familiar with that kind of spaces, L2 log of this set bar means that it is L2 log, and it is L2 for any open bounded subset of this space, right? The problem is this one, which is nearly the same without the epsilon, right? Very classical. I skip the usual assumptions on A. We take F in H-1 log here, G in H1 log. I take G in H1 log because it makes things a bit simpler, but we can take actually G in H1/2 log and just put the GL here every time for the problem, right? So it's adapted very far. This is a variational formulation, as you know. The last inequality is just to be taken in the sense of the trace theory. And what we want is to see when I make my L go to the infinite, does UL converge? And how does that converge? And to what is that converging? UL? L. L is here to define the cylinders. Every time I took... Yeah. And so what we want to see, what we want to have is that kind of convergence of the gradient of UL to the gradient of U infinite as L goes to infinity with a good rate of convergence if we can. And then we can imagine that we won't have the convergence of all the cylinder. So we want to correct it to get a convergence on all omega L with a corrector. Just some few results before going. This is mainly the first result which has been done about that by Chipot and Rougirel in 2002, where they have they fix L0 and they have a polynomial convergence. Then this result in 2008 is given by Chipot and Yeressian. It's important mainly for the iteration technique they put here and that we will see later on in the proof of the main result. This one does not have much to do with the exact problem, but still has a great importance because they introduce this technique, which is to consider UL as a Cauchy sequence, so that we can take some more general assumptions and construct the limit to infinity. In 2014, Chipot proved this result for the Laplacian and proved the general result for the homogeneous Dirichlet problem in 2016. And just a remark, which is that we can extend, supposing a polynomial growth on f at the infinite, that we can have here omega L minus eta log of L instead of the classical omega L over 2. Right? And so just before giving the result, a Poincare inequality, which is nearly the same as usual, but with this constant here does not depend on omega 1, and therefore does not depend on L. And we'll see that what we want mainly is that our constants does not depend on L at any time, right? So here is the problem. If we take F in our space defined before, G in H1 log, such as the gradient is in that, then UL goes to U infinity strongly in H1, where U infinity is a weak solution to this problem, right? So we have the same problem as for F, plus this condition on the gradient of U infinity. We'll see later on that, in fact, for both F and here, it's important that beta is not too high. And we have this estimate on the gradient, which is the result we were looking for mainly. A few remarks. First, this is the variational formulation of the problem. Secondly, if we really want to take H1/2 here, we should replace the condition on the gradient of G by this one with a given norm. Okay. And the growth condition, this one, is mandatory to have the uniqueness of the solution. Okay, I'm going fast on the proof. First thing is to prove this inequality. To do that, we define a row function, which is in 2 dimensions, it would be a plateau, you know, like 0, going to 1, and then going back to 0. With this condition of the gradient, this condition with the constant does not depend either on L1 or L, and we can have this because of the assumption that omega 1 is star-shaped. Then we can multiply this function by UL minus UL plus R, so that we have a H10 function. Since it is in H10, we can use it as a test function in the differential equation for UL. And then making this observation, right, because outside it is either 0 or 1, so the gradient is 0. We have that, okay, this one is greater than that, using the property of A. So it's equal to A gradient of that times gradient x1 row times UL minus UL plus R. Okay. So we jump to that because outside of this part, this is 0. Then we use the bound on the gradient of rho to derive that, and the property of A to have the big lambda. Then we pass here by Cauchy-Schwarz inequality, and here by using the Poincare inequality which we have. And this can rewrite this way by dividing here and here by lambda, and then considering that this is integral on omega L1 plus 1 minus integral on omega L1, putting the omega L1 part here. Since rho is 0 outside, we will have this bound, so we have omega L1 here. And so we have 1 plus the constant here, and we divide, so we have this constant minus, divided by this constant plus 1, so here, right? Then we want to bound this, and to do that, we just take the previous inequality and iterate it over and over, so that we can rewrite this way. And now what we have to do is to show that this is bounded by C exponential minus some constant. To do that, we take ZL, which is UL minus G. We make some use of the property verified by AFG, which are the ones on the function sets, right? So the bounds on the gradients. We use the property of A once again, so we have this one. And since using this inequality, because you just have plus G and minus G, this is equal to this, is less than the norm of the gradient of this plus the norm of the gradient of this, which is less than that. And combining this plus this one will lead to here. And so if beta is small enough, which is to say smaller than alpha tilde, we have something negative here. Then we show that for all positive L and non-negative T, and to do so, we just make the summation. Here we add plus I on the second line. Then C exponential minus alpha L is going as a factor. So you will remain with the sum of some terms of geometrical sequence, which is bounded by this one. And so we have this result. On the step 4, we show the existence of nu infinity. And to do so, we first use Poincare inequality to derive this. And then it means that UL can be considered as a Cauchy sequence for the norm of the Banach space H1 omega L0, which is to say there is a limit. So for every omega L0, we have a limit which will be U infinity L0. So for every K integer, we have a limit U infinity K. And by setting this one, we have our limit since it's defined everywhere, noticing that U infinity K is equal to U infinity L for every L less than K on omega L, right? So I'm just adding some parts, but they remain the same of where they are defined together. Then we show that U infinity is a solution to the variational problem. And to do so, we fix L0 once again. We use the strong convergence of the gradient of UL to the gradient of U infinity. And so we pass to the limit here, having this equality. And since this is verified for any L0 arbitrarily taken, then we actually have that U infinity verifies the variational equation that we gave in the remark after the theorem. And then making some trace operator things, right? We just show that actually the trace of U infinity is equal to G on the whole boundary of omega infinity, so that this condition is verified too. And finally, but by making this, which is to say that U infinity is U infinity minus U2L plus U2L, and using the bounds we already have, we just get the estimate, which is the last part to verify to show that U infinity is a solution. And finally, for the proof, the existence, the unicity result. Classically, we just suppose two functions which are verifying the problem. We apply what we have for UL and UL plus R in the first step. It follows that, we integrate that, we make K go to infinity, and we will have that U infinity is equal to U infinity tilde. Yeah. They are the same on the boundary. And so we have that there is one unique solution. Okay? Yeah. Just a remark, which is to say that assuming mainly the same assumptions than in Chipot and Yeressian 2008, we can retrieve their result as a special case of the theorem. Then jumping to the correctors, just two results before, which up to my knowledge are mainly what have been done on that kind of problem. The first one by Chipot and Mardare in 2008, once again, for Stokes' problem, and the second in 2010 by Chipot and Gasmia, which is very near to what we are doing, but they construct for the case of the Laplacian, and they find the corrector with which they have this exponential convergence on the whole cylinder. I just would like to point that, yeah, I know, right. But you know, there are still some things. That's why I'm hurrying. Yeah, I just want to point out that they are very helped by this assumption and the symmetry of the operator, which we don't have in the general case. So it's not just directly derived by the result, right? And the other thing is that this result is self-contained, while the general result needs the estimation from the previous theorem. So for that, we just take the cylinder being the classical one with one dimension minus LL times omega in arm n minus 1. This estimate on F, once again, we want F to grow maybe exponentially at infinity, but not too exponentially, right? Which is to say, there is a beta which has to be small enough, once again. First, we note that the perfect operator would be UL minus U infinity, since it would just give 0, so it's perfectly corrected. But first of all, there is no interest at all in that. And second of all, it's too dependent on L, so we want something which depends less on L. And to do so, we construct the correctors both on the right-hand side and on the left-hand side differently. So we will just do the right-hand side, and the left-hand side is just the same. You replace the plus by a minus, and you're done. So the corrector on the right-hand side is solution to this problem. And the corrector will belong, because there is no junction point, in H1 of omega L minus the section at the origin. But it's enough to get a H1 of the whole cylinder corrector, just to multiply by an elliptic continued function, which can be this kind of things. Okay, so first step, there is a unique solution to the problem verified by WL+. I skipped some proof because we don't have too much time to spend on that. Those are some intermediate results with some bounds that we will use. Then this theorem, right? It just says that the gradient of this function is bounded by C n exponential times the gradient of this function, but you find a way to replace the K here by L, right? To do that, we take H, which is more or less the same kind of the row before. We make a H1 zero function, we put it as a test function. We have this inequality using the properties of A, and we use some Cauchy-Schwarz and Poincare inequalities once again. So we have this, and we arrive to the same kind of inequality we had in the proof of the theorem in the previous part, which is once again the use of the iteration technique by Chipot and Yeressian. And by this, you can see that iterating it over and over, you will just get to some exponential, right? So we have this estimate, which is nearly what we want, but on the right-hand side, yeah? And to do that, we just make some use of everything every bound we've been proving before, putting them all together. Just to point here that beta appears here, and when we say that beta has to be small enough, it means this time that 2 beta has to be smaller than alpha, right? So minus alpha plus 2 beta L stays negative. And so the result, which is to say that we can have an exponential convergence on the whole cylinder by adding WL, the correctors, than we had. And once again, the gradient here is to be taken in this sense, since we are not in H1 of the whole cylinder, right? And in the important case, which will give a particular interest to the correctors, which may be the main motivation of them, actually. We just take those hypotheses. Once again, WL plus and WL minus are solution to the variational problem, which we saw already. And we say that under those assumptions, we can define the corrector by just being a translation of a corrector we define on this cylinder, right? So there is nearly no dependence on L at all anymore. The only dependence being the translation. And so what is important is this result. Just a reminder, we said that we have usually a convergence on omega L over 2. We can put that to omega L minus eta log of L. And we have this nearly optimality result. Optimality taken in the sense that we want the largest domain of convergence possible. Okay? And so we say that we can't have a convergence of a cylinder of the type omega L minus just a constant. It's not possible at all. All right? And to do so, we suppose that we can. Right? We derive those inequalities. And then we finally derive that the gradient of W plus here is 0. We use the Poincare inequality. And so W plus is 0 here, which is impossible because if we take some analytic coefficients on A, then W plus is analytic, and then W plus is equal to 0 here. So the U infinity is equal to 0, which is actually not mandatory. And there is no reason for U infinity to be 0, so this is impossible. Another way to do that being using some maximum and minimum principles just to derive the same way that U infinity is 0 and contradiction. And that's it.
Yes. Any question?
I'm clear.
What? You chose. Okay.
You can applaud me as much as you want.
At least one question should be there to the student, right? Otherwise, you have chosen that omega starting with the star-shaped. Where did you use that?
The star-shaped is to make rho in the first step. Here, to get this inequality with no dependence on L, we have to use the star-shaped assumption so that in between L omega 1 and L plus 1 omega 1, for any L, there is at least a delta distance which does not change.
So the other type of domains.
Yes, there is a minimal distance every time, at least so that we can have this band.
All right, thank you.